So delighted now to move on with the Marine Surveying Fest second edition for commercial ship surveyors. Big thank you to Mike Wall, who contributed last year. He enjoyed it so much he's come back for more this year. Mike is a name who many of you will know, not only an experienced surveyor but an author and a trainer as well. So he's picked this year Container Lashings, Failure Surveys and Failure Assessment. We're kicking this off a little bit early because, as Mike said, he's got 90 slides. So batten down the hatches for the next hour, I'm guessing, and off you go, Mike.
Thanks a lot. Here we go. Okay, so container ships, like all ships, go through ship motions. And we have 6 degrees of freedom: rolling, pitching, heaving, swaying, surging, and yawing. And all of those have an effect on containers, on container ships. The rolling affects container corner posts, Twistlocks, hatch covers, and the deck by inducing compressive and tensile forces in those areas. Pitching causes longitudinal racking in the container sides, which may be high at the bow and the stern. Heaving is induced by pitching, increasing compressive and tensile forces on corner posts and Twistlocks. So there are 6 motions. You've probably seen that diagram before. We've got rolling, we've got sway, sideways movement, if you like, the pitch, the surge, acceleration and deceleration along longitude direction, yaw, twisting and turning from side to side, and the heave, up and down. Okay, so one of the problems we've got at sea nowadays is parametric rolling, and it's becoming more prevalent, as are these massive big waves that we're getting. Now, parametric rolling is an unstable phenomenon which can quickly generate large roll angles that are coupled with significant pitch motions. The rolling occurs in phase with pitch, and on container ships introduces high loads in the containers and their securing systems. It appears that post-Panamax container ships may be particularly prone to this behavior. It's an important issue considering the large number of these vessels currently sailing. And one of the previous papers showed whole stacks of containers fallen over on the back end of a container ship, and that was because of parametric rolling. So, parametric roll occurs when natural roll period is between 1.8 to 2.1 times the encounter period, normally associated with the pitching period. The larger the flare, the more likely is the parametric roll angle and wider the range of resonance. It requires a group of waves above a threshold or critical height for parametric roll to be initiated and sustained. The threshold depends on the size and shape of the hull, bow flare being particularly important. Right, so why do container stows collapse? Well, very often it's because they're too heavy and too high. The upper containers are heavier than the lower containers in a stack. This happens regularly. Not taking wind force into account. Loose lashings, we've just been talking about that briefly. Incorrect lashing pattern and or lashings in poor condition. And the chief officer's calculations based on still water conditions and not the conditions that they should be anticipating that the vessel is going to meet. Another one, clear one, is where there's been 2 20-foot containers placed in a 40-foot slot with no double stacker fitted. This is known as a Russian stow. Then you've got mix of left and right Twistlocks, regular occurrence. Mixing of high Q and standard containers causing misalignment, preventing the fitting of double stacking cones and bridge pieces. So the actual stack is no longer a homogeneous stack. A stow consisting of all haiku containers. Now, why is that going to make a difference? Because it could be that the class stowage plan actually shows that she has 6 high standard containers, and if you put 6 haiku containers on there, you're increasing the height of that stack considerably. And then the movements of the cargo in containers. Very often the cargo hasn't been stowed in the container in an appropriate manner. It's not shored or lashed appropriately so that heavy machinery, etc., can roll around inside the containers and do damage. Then we've got stack container lashings causing shock loading, which can be 2 times normal loading. That's if you've got, sorry, slack, not stack, slack. Incorrect GM, if the GM is too high and the vessel is stiff, that causes shock loading. So these are the actual forces that are going to be experienced by the container. So you see you've got the transverse racking due to the rolling from side to side. You've got longitudinal racking due to the pitching. And then with heave, you've got compression in the main posts here. So these are the maximum allowable container stresses, which are given by class. So 34 tons, 34 tons, 50 tons in the bottom, and 50 tons here. These are the transverse compressive forces. Then you've got the vertical corner forces. So in the castings here, 15 tons at the top and 20 tons at the bottom. And compressive forces, 67.5 tons and 67.5 tons. And the corner lashings, of course, casting lashing forces here, 15 tons, 30 tons, 30 tons, 15 tons. Okay, they will be important later when we start doing calculations. These are the sorts of forces you get in containers. This compression force, this is where the upper containers are being too heavy and the vessel has been rolling, and consequently the lower container is crushed. Then we can get racking force, again, where the lower container is racked. Okay. Then we've got separation forces, so as the containers roll over, the Twistlocks here and here, and the stacking corner here may give way due to the loads. And in this case, this is the transverse forces where the buttresses have held, but the containers themselves have moved quite significantly due to the motions. So for those who aren't familiar with container stowage, this is the numbering system for tiers and slots. So we start with the slots at the top and you work from the center outwards to port and starboard. So they become 2, 4, 6, and 8, and 1, 3, 5, 7. This is a small feeder container vessel, which was on the Hong Kong to Philippines trade. And then the actual tiers themselves are inside the hull. They start with 0, so there'll be 0, 2, 4, 6. And inside the hulls nowadays, of course, you can have 10, 12 high. And on the deck, this is what differentiates them, is there's an 8 in front of the number, so 8, 2, 8, 4, 8, 6, etc. Now, as far as the bays are concerned, the bay numbering is interesting, because remember, you can carry 40-foot containers and you can carry 20-foot containers. So in this particular case, the 20-foot containers are 1 and 3. Then they would be here 5 and 7, 9, 11, 13, 15, and so on. And where there are 40-foot containers stowed, it becomes 2, 6, 10, 14, 18, 22, 24. So if we look at the actual the identification, they're identified by bay number, by tier, and by slot. For example, 268603. So 26 will be bay, 86 will be tier, and this will be the stow. Okay, moving on. So this typical lashing arrangements for a container ship like this. This is a little feeder vessel, again, Vietnamese vessel actually at the time. So you see the numbering as before, and then you see we have cone pieces, or supposed to have cone pieces at the bottom here, and then Twistlocks between the containers, and then obviously bridge pieces between the containers themselves. Down below, of course, there is not much need for the bridge pieces, etc., but they will have Twistlocks or stacking cones to separate them. Okay, and this is a typical bay plan for that type of ship. And you can see it's signed off by the chief officer, and he will probably use a coloured crayon, Crayola pen or something to mark in the different ports for the different slots. This is a typical little coastal feeder vessel operating out of Hong Kong. So what sort of securing arrangements we have? Well, we have Twistlocks, we have lashing bars, we have turnbuckles. We'll be looking at these in the pattern later. or known as bottle screws by some. I think turnbuckles is American, we're bottle screws. Stacking cones, single and double. Lashing D-rings on the deck and on the hatch covers. Shoes for the base Twistlocks. Bridge fittings to tie them together at the top. And buttresses that tie them to the side of the hold. And then various other mooring points around the hull. And these are some of the fittings you'll find. You'll see them on board the ship. These are the bridge pieces that we were talking about, which slot across between containers. Same here. Then these are the stacking cones, a single and a double, etc. Okay, you'll get this presentation later, so you'll be able to see these in more detail. Then, of course, you've got the bottom foundation fitting. So these are what you'll find around the deck and the hatch cover to hold the containers down or in position on the deck or on the hatch cover. These are the D-rings, cone pieces and Twistlocks. And we'll talk about Twistlocks a little bit further later. Then again, we have between the actual containers, various types, and on the deck as well. Stacking fittings, and again, bridge pieces again. Okay, moving on. This is a standard sort of type of lashing now this is on a vessel which is obviously not a dedicated container ship. And the problem we had going back to some years ago was that many general cargo ships had been converted over to carry containers. And these were the vessels where we had most of the problems. And this is the linkage plate, the double linkage plate I was telling you about. So if you're putting two 20-foot containers together, you must put this between the two containers in these positions here. We're talking about the vessels that had been converted over to carry containers, general cargo vessels. So what would happen is they would have maybe fixed guides at the forward end of the hatch or the after end of the bulkhead, and then in the middle of the hull they'd have these temporary or portable guides which were held in place by stays, by wires and stays. This one in the middle here would be to allow 20-footers to be put into a 40-foot slot. Okay. And this was another one where we had problems with temporary container stacks and guides. So this is looking down a container hull showing the cell guides. So here's your cell guides. So you've got 1, 2, 3, 4 across here. So this would be 2, 4, 6, 8. And then it would appear that you've probably got about 4 high, maybe 5 high. You notice that the tops are painted yellow. These are to help the container crane driver to locate the containers when he's dropping them in. And there's the hold ventilator and access hatch. And you'll see he's got the lashing bars all set up ready for the deck. And this is a typical feeder vessel in Sheko, Yulian Dockyard. Hatch covers obviously ashore being maintained, painted, repaired, etc. And this one is an interesting one because you'll see that these are 40-foot, obviously, holds, container holds, but halfway down you've got these hinged cell guides which will roll out in this direction, so you can put 20-foot containers in these two tiers here, 2 stacks here, and the same in this hold here. Okay. Very popular. Now we're going to look at the actual gear. This is a twist lock in the locked position. So that's a right-hand twist lock. It's right hand when it's locked in the right-hand position. In the left-hand position, it's open. So that's a right-hand one. Now, very easy to confuse these. So there you see the right-hand twist lock in the open position. Okay. And this is a twist lock with both sides open. These are actually operated by a claw on the end of a pole very often to lock them. And it's being pulled the other direction. You see it's now locked. This will lock automatically when it's dropped into a slot. So let's look at the lashing arrangement. This is a standard lashing arrangement, class approved standard arrangement. You'll see that lashing bars are passed from the lower left corner of the third tier to the deck, to the D-ring on the deck with a bottle screw, and the same on the other side from the lower right one to the left-hand side here. And then you have, again, lashing rods again from the bottom of the second tier container, so crossing over here. And that is the correct way. And of course, you've got twist locks in between these containers here, and then cone pieces here locating the containers on the deck. Okay, that's the correct way to lash them. And here we have the second tier is already in, and you've got the lashing bars into the second tier. Bottle screws in place and lashed to the D-rings on the hatch cover. These are the same ones, but now what they've done is they've got the second tier in, but they've also got the third tier with the long lashing bars and bottle screws. And again, these are actually extenders to allow you to extend the length of the lashing bars. There could be that there's a haiku on the top here, and that's what these are for. Okay. And you see the access grating here. These are supposed to be, if you're doing a survey on a container ship, these are supposed to be accessible, readily accessible, and also with handrails to prevent the people doing the cargo stowage, etc., from falling over the side. So safety for the crew and the stevedores. These are what we call penguin hooks. So this is how you actually locate a lashing bar into a corner casting. And you'll see they've got the pulls here for twisting them into position. I'm sorry the photographs are so old, but I haven't been on one for a while, but there we are. Anyway, this is these are well-maintained bottle screws, but at the same time, they're actually screwed down to almost their full extent. And really what should happen is that they should be only screwed into about this depth here to give you the adjustment during the voyage to maintain the tension in the lashing bars. Okay, you see there's a locking nut here. So once they've been tight tension, locking nut is applied here to stop them from unscrewing. Okay, nice D-ring, there's nothing wrong, shackles okay. These are the bridge pieces we've just been talking about. So this is how they're fitted between the tops of the containers. Okay. So what adverse factors? Well, we talked about the causes before. So stack weights and weight distribution have got to be appropriate. But calculations have been carried out on still water conditions, not the actual weather conditions the vessel's going to be experiencing. Adequate strength of the hatch cover. Can the hatch covers actually take the weight of the containers? Slack container lashings, causing shock loading, which can be 2 times long. We've mentioned this before. Key one, poor condition of lashing equipment, not correctly maintained. These, usually the container lashings are actually anodized to prevent them from corroding, but because they get damaged occasionally, then they start to corrode. And then of course we mentioned the incorrect GM before and overloading of stacks. And then the incorrect distribution of container weights. Now, computerized loading programs can help in preventing the overloading, etc. Now, in Hong Kong, at HIT, excuse me, they had a program that showed the actual containers being moved from the quay across onto the ship. And you could see the weights, etc. They were all recorded so that they knew which weights were going where. They never lost a container and never had a problem in all the years that, I think it was 29 years. Records should be maintained of all equipment on board and the condition. So the chief officer should be keeping a lashing gear record, logbook. So there should be sufficient on board for the full container load with additional spares because of possible damage or loss. They should be regularly examined for distortion, buckling, corrosion, cracking, or excessive wear. Turnbuckles, twist locks, and bridge pieces to be regularly lubricated and the Twistlock springs to be checked. All fixed fittings to be examined, particularly D-rings, and a file of certificates of approval retained on board. The class certificate, class surveyor, and possibly P&I surveyor will ask to see those. Any suspect fittings to be immediately replaced. That's why you have the spurs on board. And we mentioned the reasons. We said this already. We've done this. Yeah. Yes, we mentioned this before. Sorry about that. Duplication. Okay. So here we have a little coastal container vessel operating around Asia, Southeast Asia. And so you've got the container associates. So they're actually 6 abreast and 3 high. And you can see the actual lashing bar here to the 3rd tier, and then the 2nd tier lashing bars here. Okay. There's a container being discharged already. Okay. So this is what the cargo, the class cargo plan, the stowage plan showed, right? So it showed actually lashing bars to the top of the lower tier, the bottom tier, and lashing bars to the bottom of the 2nd tier, and then a diagonal to the top of the middle one on the right side there, the same on the other side. Okay. These were all lashed to D-rings. Okay. And this is the actual stow that I found when I came on board. So you'll see that there are lashing bars missing to the top of the lower stow, right? But they have actually done the 2nd tier ones. They thought that was enough. And those are the actual lashings. So there's a deficiency in the lashings there, okay? And so they are actually using right-hand twist locks, not a problem, as long as they're all the same, and they are both right-hand there. And then you have a right-hand and a left-hand. Okay, and we're starting now to look at the D-rings as well. They're not looking the best. Okay, and then you can see this D-ring is starting to become deformed, but the bottle screw is not so bad. It's in place, it's okay, but the D-ring is failing. And then of course you have a D-ring which is turned into a, sorry, go back one. You've got a D-ring that's turned into a G-ring, which has just been torn completely away. And the crew have decided, oh, well, we'll just hook it onto the top of that, not a problem. And there's not even a correct pin in here in the actual lashing there. And there's another one that's turned from a D-ring into a G-ring. Okay. And, oh, well, I mean, that speaks for itself, doesn't it? Obviously, the D-ring's gone, so we'll just make do with, oh, this pin will do, won't it? There we go. Instead of the usual fitting here. Speaks for itself, I think, that one. Anyway, so moving on. The other problem you have very often is the mixture of stows. Sorry. And so here we have actually 45 footers, okay? We have standard 40 footers, and then we have standard containers, and we have haiku containers. And in fact, the lashings haven't been put in here yet, but you can see this is not going to be the best possible stow. There's going to be problems here. So then here we go again. We've got, instead of having the correct pin in here, we've got just a piece of bar shoved through. As soon as that starts jumping, that pin is going to drop out. There's going to be no lashing there at all. So underdeck collapse stows, why do they happen? Well, buttresses not fitted or fitted incorrectly. Vertical movement between stacks causing double stacking cones to fracture. Adjacent stacks of different types preventing fitting of double stacking cones. So this is where we're talking about a mixture of haikus and standards. Gaps created by empty slots preventing transmission of forces across adjacent stacks to the buttresses. And this is the double stacking cone that we just mentioned before, and this is how they should be fitted between two 20 footers. Okay, this is actually the confirmation of it. And if you've got, obviously, different heights of containers, so you've got a 40, a standard and a 40 haiku, they're not going to align, so you can't actually put the piece in. So that could be anything from 6 inches to 8 inches, 18 inches difference. Of course, as you get higher, and if these are all standard height, and these are 45s, that could be 4 or 5 feet difference. And this is one where the captain said, "Oh, we had a good GM," and these fell over. The reason they fell over was because the GM was too high. The vessel was very stiff. This was because they're on a feeder trade around the Southeast Asian ports, and they're supposed to, they're supposed to deballast the ballast tanks when they're in the loaded condition, and of course they didn't, and as a consequence, the GM was high and the vessel was stiff. So not only did she have an adequate GM, she had an excessive GM. So these are the rules which are applied by the classification societies for freight container securing arrangements, and this is the Lloyd's one. So all container vessels are subject to approval for the lashing gear, lashing arrangements, the stowage arrangements. And what happens is class considers the lashing system taking the maximum or the worst conditions into consideration. That is a maximum wind speed of 40 meters per second, a maximum roll angle of 30 degrees, pitch not exceeding 8 degrees, and a heave of length between perpendiculars between 80 divided by 80. And then obviously the maximum weights of containers that would be possible. And also static gravity forces, inertial forces due to roll, pitch and heave motions of the vessel. So this is what they take into account. Oops, sorry about that. Let's get rid of those. Let's do it again, come on. There we go. The forces imposed by securing arrangements, they take those into account. The wave impact forces striking the containers, wet, green seas coming over the bow and over the sides. Calculations are relating to 4 high stacks only, although they've now increased them to 8. This is with containers at the extremities of the vessel, so this would be right up on the bow, number 1, and on the outside of the vessel. So bay 1, right on the outside port starboard sides. Or if it's a vessel with containers aft of the accommodation, then it'll be the after ones right on the port starboard side aft extreme. Oh God, here we go again. Sorry about this. There we go. So we've looked at this before. Let's move on. Now that was for 4 high. Now this is what's happening. Of course, we're getting container stacks a lot higher now. So what is happening, of course, is the ship designers are putting container bridges in so that the bottom 2 containers are basically held down by the top 4, secured by the top 4, and the calculations are now done for these 4 here. These are, I'm sorry about the fuzziness here, but these are some of the symbols used. So this is looking at the pitching situation, so the distance from the centre of flotation and the height above the centre of flotation. That's for pitching. This is for rolling, so again we put it right on the outside in the extremity, and see this is the height above the centre of flotation and the distance, the Y and Z axes. So other things to take into consideration, the forces in the forward 0.25 L, the quarter length, are increased by 20% to take into account wave impact and shipping green seas, unless the containers are adequately protected by a breakwater or some similar device. The resultant force acting on a container is the vectorial sum of the individual directional components of all forces acting at a given instant. These calculations again are based on the most severe combination of the forces. Oh, why is it doing this? There we go. So if we look at the bottom of motion, so this is where the ship has just gone over a wave and is now coming down She's going down to the lowest possible point. So of course you've got and she's rolling as well at the same time. So you have a static rolling force, a rolling dynamic force, and a heave force. Oops, sorry. And on the bottom, inside the hole, of course, you've got the same thing here. So you add these vectors together, and you'll get a net force for the one on deck and one below. See here, the forces here are far more significant than ones down in the lower hold. And the same with the top of the motion. So she's just coming up to the top of a crest of a wave. And you'll see as she comes up, there's still a roll static force as she's moving over to port here. There's a roll dynamic force. There's a heave because she's going up. And she may have wind as well. So you start adding those together and you'll get the vector of all the forces. And again here with the top of the motions down inside the hold, you can see the combination of forces here. Okay. So we've already looked at these container stresses. This is what they are class of considering. And the 40-foot containers, the 20-foot, the normal numbers are for 20-foot containers. The ones in brackets are for 40-footers. So we've seen that before. This is for 20-foot or 40-foot. And again, these are the maximum allowable container stresses in the main members of the container. So 15 tons racking, 10 tons rolling, pitching, and again 15 tons here. Okay, they're the racking loads. Okay, these are the calculations, and I'm not going to go into them. I'm just showing you how complex they are. So they're working out the static roll pitch combined, the dynamic roll pitch, the heave, etc. These are all figures taken, numbers put in here and then worked out, which I have done actually with a spreadsheet. And then these are the design breaking loads and proof loads, which you have to take into consideration. So for a rod, a mild steel rod, the maximum is 3 times safe working load, high tensile steel 2 times safe working load, etc. So that's taken into consideration. Then, of course, each of the actual fittings used, they have recommended minimums and maximums in tons. So safe working loads, the proof load, and the breaking load for each of those pieces. And then the actual container lashing gear and fittings. These also have recommended loadings. And then what we do is using the ship motions for roll. The maximum, as you said, is 30 degrees. So that is the period in seconds is given as T equals 0.7b of the square root of GM. Pitching here is the time for pitch is 0.5 times the square root of LPP. And the heave is LPP divided by 80. And the time is 0.5 times the square root of LPP again. And this is where we start to do the calculations. Oops, sorry, so I'll go back one. And you can see they start to get quite involved. And if you've got to do those over and over again, it's going to be a real pain in the backside. So let's move on to what the surveyor is going to be doing. So the surveyor will photograph and record damage to the vessel and the lashing gear. This is just the damage surveyor. But the actual consultant who's going to be doing the calculations to work out the stresses is going to retain damaged lashing equipment for metallurgical testing for latent defect and load testing later. To prove, this is to actually prove when they've done the calculations to prove what's happened. They then inspect the containers and the contents to ensure the contents were adequately lashed and shored to prevent movement. And they detail the damage to the container contents. They list it. And get a statement of facts from the officers. Okay, sorry about this. Here we go. So we're now going to do the calculations. So as we said, surveyor will photograph and record the damage. Retain damage lashing equipment for medical. Information on all containers involved. So the previous surveyor was the damage surveyor. This surveyor is going to be doing the calculations. So you get all the information on all the containers involved. So what their dimensions are they haikus, are they standard, are they 40s, 20s, 45s? The weight, what the total weight is, the slot that they're in, and the lashings. A bay plan to show where they are. And the vessel's general arrangement, capacity plan, and midship sections. So there it is. There we go. Then what we've done, or what I did going back many years ago, and I've used it many times, is I took the Lloyd's Register calculations and transposed these into a spreadsheet. And then what I did was, instead of inputting the worst case scenario, I input the actual conditions. So I did many container damage surveys in Hong Kong, vessels coming in from various ports around Southeast Asia, with stows and stacks and what have you collapsed and over. And the P&I clubs were getting pretty concerned about it, so they asked me to have a look at it. And what we then do, of course, is into this spreadsheet, instead of putting the maximum conditions that Lloyd's Register do, we put in the actual wind speed based on the Beaufort scale, the actual roll angle as reported by the officers, the estimated pitch, the estimated heave, the actual weights of the containers, and the actual distance of the container from the LCF and VCG. This will affect the moments of, acting on those containers. Okay. So just go back here. The further you are from the LCF, as we said, if you're up at the front of the bow, then you're going to get more forces, higher forces on it. And of course, the higher you are from the VCG, you're going to get higher forces. So then we get the vessel's particulars, load port stability calculations. So we're getting the chief officer's calculations here. And then statement of facts, including the weather conditions experienced. Of course, we can always back that up and prove that that was the case by obtaining a synoptic weather report. If necessary, we interview the bridge officers, because they can then confirm roll angles, etc., or roll periods and things like that. The vessel's general arrangement, capacity plan, and midship sections. Sorry, here we go again. And what's coming here? Here we go. So what happens now is we then put in this is the data input side, the container number, and this is tier 1, the slot, it's the bottom container. Container number 2, the position tier 2, number, slot, and you'll notice we're putting the weights in, 20, 20, 18.1, 18, 10. So that's the top 10, 18, that's not bad, 18.1, 20. So the heaviest one's at the bottom. And then this is the length between perpendiculars of the vessel. This is the longitudinal distance from central flotation to the center of volume of the container. This is the transverse distance from the central line to the center of volume of the container. And this is the vertical distance from the center of flotation. And you'll see they vary, obviously, with height here. Then we also put the container dimensions in. This is obviously a 20-footer. Breadth 2.4, 8 feet, 8 feet, and the wind velocity 15 seconds. So they're all 20-footers. Okay, so that information gets put in. And then what happens is we get the output. So here are those containers that we just actually looked at. So 1, 2, 3, 4. And again, the input data here. Okay, we noticed that we've mentioned we put the GM in here, the breadth of the vessel and the LBP, so we can work out the roll period, the pitch period, and the heave period. Okay, and on this side here is actually the output. These are the results, right? So what we do is the figures in brackets here are for 45 foot containers and 20-foot containers. And you'll see that the maximum load here, for example, 67.5 or 40 tons. And so then by putting in the actual figures, we can work out what the stresses are in the Twistlocks. so which shows the shear forces in the corners, racking forces, which are okay. And then we get down to the compressive forces, and then maximum for the combined motions per bottom corner. As you can see, this has exceeded the limit here of 40 feet by 40 to 43.73. Same over here, instead of 15 tons, we've got 19.13 tons. And interestingly, what obviously has happened here is the Twistlocks have all failed. The container stack has fallen over and the Twistlocks have failed in these particular locations. Okay, this will be available to you later. Now, the spreadsheet itself is brilliant because you can carry out what-if analyses with it. And in certain cases, you can prove that Twistlocks were not secured. So, so if you have, say, a Russian stow and two 20-foot containers gone over the side, if the Twistlocks had been in place, the loads would not have been exceeded. So clearly the Twistlocks weren't secured. You can prove crew negligence, for example, poor stability and lack of maintenance. So the poor stability obviously is a stiff vessel because they haven't emptied the double bottom tanks. And lack of maintenance, the actual lashing gear is in poor condition, so it fails. Proving inadequate lashings as a contributing factor, so they haven't put enough in, as we saw before with that small coastal feeder. Proving poor stowage as a contributory factor, and proving that weather conditions were not contributory. So because we put the actual weather conditions in, if that spreadsheet, those results that come out don't show any loads being exceeded, then clearly the weather conditions were not the problem. And then, of course, synoptic waves and parametric rolling, we can then show that that has had a serious effect. And of course, carrying out what-if analysis. So we can vary certain inputs into the spreadsheet and see what happens. Sorry about this. So, marine surveyors and consultants need to be innovative. And I know several surveyors at the moment who are looking at different aspects of surveying and trying to find new ways, innovative ways, and software which will do the job automatically or more easily for them. The information is out there for us to use. It's there in the public domain. So just like me, I use the information from the classification societies. I have no qualms about that because they have imposed in our domain. So I've got no qualms about using their information. There we go. So this is a recent container stack height. I think this is an OOCL vessel in Hong Kong. So she's 1, 2, 3, 4, 5 high. But look at the problem here. You've got haiku, oops, sorry, go back. Haiku, standard, when it's a smaller, shorter haiku than a standard at the top here. These are all haikus. And we know the haikus by the yellow and black striping on the top edges. Which, you know, there's no way you're going to be able to put bridge pieces up here. So you're basically relying totally on the Twistlocks and the lashing gear. And you can see the lashing gear only goes to the second tier. There's only one lashing bar to the third tier. And these are some of this is a current container stack, height 22 wide by 8 high. They're even higher than that now. In fact, this is what we could be seeing in the future, 13 high by 13 wide. So I think that's me. So as you can see from what I've shown you, necessity may be the mother of invention, but an engineer is usually the father. Thank you.
Thank you, Mike.
You may have seen my reaction there.
Crikey, we were all aghast.
I thought I wasn't going to get that in, but I did.
No, you've done really well. That last slide was extraordinary.
Yes, very much so.
And I mean,
that's actually a computer-generated graphic, but it's not within the the realms. You know, it could have happened fairly shortly.
So the question, I suppose, for me is how many more containers can we get on ships? How big can those ships become?
Well, they're up to, well, as we saw from the earlier insurance presentation, the alliance presentation, they're up to what, 24,000 now?
24,000. Yeah, extraordinary. Does anybody have any questions for Mike?
No, thank you very much. Bye bye.